Continuing with our discussion on atomic and nuclear physics, we now have the examples part of our discussion, examples of what we have covered so far. So examples part 1. Consider the following problem. Example number 1. For the hydrogen atom, how many possible quantum states correspond to the principal quantum number n is equal to 3? So n is equal to 3. Quantum number L is equal to 0, 1, 2, and so on up to n minus 1. So n minus 1, 3 minus 1 is 2. So L is equal to 0, 1, 2. Quantum number M is equal to negative L plus 1 up to positive L minus 1 and then positive L. Since L is 0, 1, 2, for each value of L, you have a value of, set of values for M. So for L is equal to 0, there's only one value for M. M is equal to 0. So that's one state. For L is equal to 1, M is equal to negative 1, 0, 1. You have 3 states. L is equal to 2. You have M is equal to negative 2, negative 1, 0, 1, and 2. So 1, 2, 3, 4, 5, 5 states. So 1 state, 3 states, 5 states, 1 plus 3 plus 5, that will give you 9 possible quantum states for the quantum number n is equal to 3. Next, we have the following problem. Example number 2. Calculate the angles that the angular momentum vector L can make with the z-axis for L, small l is equal to 1 as shown in the figure. So z-axis, angular momentum vector L, 3 possible locations, L, L, and L. So calculate these angles with respect to the z-axis of these 3 possible values of L. So you have L, theta 1, then L, theta 2, then L, theta 3. For L, small l is equal to 1. Now, the angular momentum L is given by square root of L times L plus 1 h bar. Since L is equal to 1, L, substituting small l into the equation for capital L, angular momentum is just equal to square root of 2 times h bar. Now, quantum number M is equal to negative L plus 1 up to positive L minus 1 and then positive L. So using this, L is equal to 1, we have M is equal to negative 1, 0, and 1. LZ, the Z component of the angular momentum vector L, is given by mh bar. So that means if there are 3 possible values for M, there are 3 possible values for LZ. negative h bar, 0, and h bar. In terms of since rather Lz is the z component of L, from the figure we can use Lz is equal to L cosine of theta. So for instance, in this L, this is Lz adjacent to angle theta, so we can use cosine theta is equal to adjacent over hypotenuse. That will give you Lz is equal to L cosine theta. Lz, you have three possible values, negative h bar, 0, and h bar, whereas L is equal to square root of 2h bar. So for Lz is equal to negative h bar, we'll be able to calculate theta to be equal to 135 degrees. If we use Lz is equal to 0, we are able to get theta is equal to 90 degrees. And then, if you use Lz is equal to h bar, we are able to get theta is equal to 45 degrees. So the three possible angle values for the angle are 135, 90, and 45 degrees. Comparing these values to the figure, you have theta 1, theta 2, and theta 3. That means theta 1 is 45 degrees, theta 2 is 90 degrees, and theta 3 is 135 degrees. Lastly, we have the following example. You have a hydrogen atom in its ground state. It is placed in an external uniform magnetic field. B is equal to 1.5 Tesla. Determine the frequency of radiation produced in a transition between the spin up and spin down states of the electron. You have Ms is equal to 1 half, Ms is equal to negative 1 half. So spin up and then spin down. If there is radiation produced from spin up state to spin down state, what is the frequency of that radiation? In other words, what is the frequency of the light emitted when the electron transitions from spin up to spin down state? Now, the potential energy associated with interaction between the electron magnetic moment and an external magnetic field is given by the following equation. U is equal to negative mu zB. Mu z is just positive, negative mu b. So negative mu z will give you negative positive mu b, and then times magnetic field B. So this is the potential energy if we let U initial to be negative mu BB and final potential energy be positive mu BB. Final minus initial will give you the change in the potential energy. Absolute value of the change in the potential energy from this will give you 2 mu B. This will be the energy of the photon that will be emitted by the hydrogen atom when the electron goes from spin up to spin down state. Spin up plus spin down minus, for instance, or vice versa. Spin up minus mu BB, spin down positive mu BB. So from spin up to spin down, the difference in the potential energy is 2 mu BB. Therefore, This difference in the energy will be the energy of the photon released. Now, photon energy, you will recall, is just equal to hf. Knowing the equation for E photon, we can isolate F and calculate the frequency of the emitted photon to be 4.199 times 10 to the 10 power hertz. So that's it for now. In the next video, we'll continue our discussion of atomic and nuclear physics by looking into the concept of the photoelectric effect. So thank you for watching.